Okay, the next speaker is Thomas Sinclair, and he's actually no. What was the title?
Okay.
Dimensional operator spaces. Thank you, Chris. Yes.
Index. Yeah. There we go. Right. So, thank you very much for the opportunity to speak at this workshop. Sorry about getting the abstract in super late. I wanted to do something with more connections with logic than this, and I have some things to say, but they were not kind of quite ready. So I'm going to give this talk that I've been giving for a little bit now. There's lots of interesting questions, I think, that are floating around, some of which are probably more tractable than the quasi-trace problem. And some of which, well, at least one of which I think maybe isn't. So let's get into it. So this is joint work with Roy Ariza, who is a former PhD student of mine, and Colton Griffin. So Colton was a undergraduate at Purdue, actually. And this transitioned from an undergraduate research project that we had previously done. So I'll talk a little bit about that, and I'll kind of get into the heart of it. So yeah, there's some things that I need to define maybe just quickly. I'll just say what operator systems are. So let's just quickly talk about what operator systems are in case you haven't seen this before. So an operator system is just some closed self-adjoint subspace of the bounded operators, which contains the unit. And that's still not enough information because, well, that's the space, but then you have to define the category. So we look at matrix amplifications over these. So these are normed spaces just from the operator norm. So you can embed the matrices over this into the matrices over the bounded operators, which is again the bounded operators on some full direct sum. And there's a norm structure. So there's a multi-level spatial structure with a multi-level norm structure. And if you have linear maps between operator systems, the correct category here is, well, okay, so there's a norm structure, there's a positivity structure. So the positive, maybe I'll just say that first. Because they're self-adjoint and unidal, the positive part is spanning. So the positive cone is spanning. It's the complex span of the positive part is the operator system itself. So you have positivity at every level. And so the correct category for linear maps are the completely bounded maps. So the ones where if you take the matrix amplification, it's the correct thing to do here. Identity on Mn tensor phi from Mne to Mnf. So the norms of these things are uniformly bounded. That's the CB norm. And because we really have star structure and unitality, really the positivity is important. So completely positive maps. So positivity preserving at all levels. So and there are lots of examples of interesting maps, even for simple cases. that are not completely positive but are positive. So for instance, just the transpose map from M2 to M2 preserves positivity, preserves the positive semi-definite cone, but not completely positive, not even too positive. And that's in quantum information theory, that's EPR basically. Einstein, Podolsky, and Rosen, so this is entanglement, more or less. Okay. So that's the category that we're going to be working in. And what is the genesis of this? So how did this start? Well, maybe some just very simple examples of operator systems. So if you have a graph, just a simple graph, no multi-edges, no loops, something like this, finite graph. You can construct an operator system, or you can construct a couple of operator systems. So this SG, this is in MN, where N is the cardinality of the vertex set. So these are just all of the matrices which are supported on the graph. So they're 0 if I is not adjacent to J, meaning it's either I is not J or they're not, it doesn't form an edge. And you can do the same thing with a slightly smaller subspace, this E sub G. It's the same thing. But then we also want to stipulate that the diagonal entries are all equal to each other. So these are very simple looking operator systems. They're just subsystems of finite dimensional operator algebras. Yet, in all honesty, these things are actually nearly as complex to study as just general operator systems. And I'll try to motivate that remark here in a second. But there are these operator systems, and then from these you can construct sort of dual ones. So dual positivity structures, and the positivity structures here are from projecting, just taking the orthogonal projection down to the subspace. Okay, there's a natural inner product here given by the trace, the Frobenius inner product. So you take the positive cone, or I should have done it the other way since I named them in that order. So you just take, at every level, you just take the positive matrix cone and you just take the orthogonal projection down. And you get a larger cone structure on these things than the cone structure that's inherited. And this is, for these examples, this is the quotient structure. And already you get sort of universal free product behavior that comes out of taking the quotient structure on these things. So there's already interesting complexity that's apparent. But I think just a general problem here is, okay, these cones are actually different, and the difference between the cones in general is lack of injectivity. So really coming up with nice ways of quantifying injectivity, and I'll just say in a sec what that is, but the operator system would be injective in this case if the projection we have some subsystem of the matrices. And we take the projection, just again with the Frobenius inner product. Which way do I want to do conjugate linearity today? I guess I chose that one. So you just take the projection here, and the question is this completely positive? Okay. And in general, the answer is no. There's very simple examples you can do just for this graph system. Corresponding to this very simple graph, just 3 vertices in a line. There it is. So this can't be an injective subsystem of M3, because if it was injective and this projection was even too positive, Choi-Efros tells you that there's a C-star structure on this. So there's a C-star structure, and you have these non-unital but nonetheless copies of M2 in the upper left and lower right corners. So the C-star structure on those two things is preserved. So you have 2 different copies of M2 in this purported C-star algebra, but it's 7-dimensional because there are 7 asterisks there, and that just cannot be, that doesn't work. There are, generically these things are not injective. So quantifying how far these things are from being injective, defining like good metrics. This again has some connections with logic, at least in my thoughts, because this was like, okay, what are sort of definable analogs of injectivity for operator systems or operator algebras? Or is there some way of metrizing things in some way, just quantifying, like taking finite dimensional things and making them injectivity sort of a metrically describable notion, like degrees of injectivity.
I have a question.
Sure.
Are you talking about hyperfiniteness when you say finite dimensional things? I mean, injectivity has several equivalent formulations.
Yeah.
So which one are you referring to?
Well, just injective in the category of CP maps, which just means that there is a completely positive projection from the bounded operators onto your operator system. Yeah.
So where would definability fit exactly?
Well, that's not a definable notion. But trying to come up with a degree of like how far are you from being injective, quantifying injectivity in some way, and in a way that is kind of compatible with ultra products, right, would be something that...
Right, I can impress you're asking whether something axiomatizable, yes?
Yeah.
Yeah. Well, what's axiomatizable?
Yeah.
Thanks.
So I didn't mention that to the undergrads, but like you can kind of play around with these things at the matrix level and try to get ideas. And we did come up with some sort of way of coming up with a metric for how injective things are, and that's all in a nice little paper that we wrote. But I think it's a much broader question, and it's not a very concrete question, and you just let your imagination run wild. What does like almost injectivity mean to you? And see where it goes. Yeah. But so that was one genesis of this line of thought. So back to the difficulty of understanding even these matricial systems. I mean, there's lots of room, actually. The point of this talk maybe is there's lots of room down here at the bottom. We don't have to think about infinite dimensional things. Finite dimensional things pose all sorts of very hard problems. So here's a favorite problem of mine at the moment. And this also, okay, there's some connections with logic here. But if we look at the complete graph on n vertices, so we have, let's just call En the E of this complete graph. So this is really all of the matrices whose diagonal entries are constant. So these are like the positive ones are like probabilistic correlations or something like this. And you have this dual structure where you quotient out basically by the diagonal matrices of trace 0. So this is isomorphic to Mn modulo diagonal trace 0. So it's some sort of projective cone. So if you think about the completely positive maps between these things, so maps from like the E's to other E's, or from the duals of the E's to other duals of the E's, those are all very boring. You can figure all of that out. But describing the completely positive maps here is extremely difficult. So for n greater than or equal to 3, what is the complexity? So this is a problem. Complexity of this set. Classical model theory question maybe, is this set semi-algebraic? No clue. That's stronger than Kahn embedding. Okay. So if it wasn't semi-algebraic, that would be stronger than Kahn. So you get into extremely deep questions about the nature of objects. Even for n equals 3, I have no idea what the structure of this set is.
So to be clear, you want some uniform definition across all ends?
Well, I mean, are any of them? Is n equals 3 even is interesting. If n equals 3 is not semi-algebraic, that's crazy. That's a crazy strong thing. Okay. Maybe there's something that can be done here with classical model theory. Why am I not saying continuous model theory? Why is that no help? You can't really talk about semi-algebraicity because so you can do a model theory for op systems. I'm trying to just kind of cram in logic in any way I can in this talk, so it's going to be kind of random. So here, the quantifier-free definable things are actually statements of this form. Maybe I'll just phrase it as these are positivity checks for expressions of the form in B of H min tensor, your operator system. So I guess evaluating it in an operator system. So you start off with the quantifier-free things being matrices here. So the A1 through AN are bounded. These are self-adjoint bounded operators. So you start off with the A's being matrices, and you can take limits, uniform limits. Uniform limits of definable things are definable. And when you take the uniform limits, you get the min tensor. So you have min tensor of B of H sitting in there, and that's too much stuff. You would just only like the linear matrix inequalities, not the linear operator inequalities, to be definable if you ever want to take a crack at something like this. So in that case, you really want the classical ultra product. But then, okay, you have to work on operator systems over real closed fields, which seems like an interesting thing to do. I don't think anybody's done it. So here's another problem. What can you say about op systems over real closed fields? There's some interesting work of Andreas Thom and his collaborators about a year or so ago, where they showed that the set of copositive matrices wasn't definable with linear matrix inequalities using some very basic classical model theory. But then you get into real closed fields. You can't work over R. That's why we take the metric ultra product usually. So we don't deal with this business.
To be clear, Thomas, when you asked about city algebra, you're thinking of understanding this over.
Well, yeah, I mean, if I'm talking about a model theoretic approach, right? Yeah, you would want to understand what these things look like as subspaces of products of some real closed field, and then maybe you can find some exotic automorphism or something that moves it around, which would show it would not be definable or something like this. But yeah, you need to access some sort of broader, or actually, well, more automorphisms, less definable things. Too many things are definable in continuous logic. It's a blessing and a curse. Okay. I think I've gone way off the map. Let's talk about index. Yeah, I'm not going to eat into anybody's lunchtime, don't worry. So that's just some things that are sort of ancillary, or things that were sort of in my mind, even though it may not be apparent from the rest of the talk, that are kind of motivating some of these things. But and maybe that's just a state of just a comment on, okay, I lost half my screen. Go away. That didn't work. No, there we go. Okay, you just press enough things randomly. Okay. So, let's talk about index. So this notion is kind of a simple or naive definition, but it again leads to kind of interesting places. And so I'll try to explain it and then loop back to what I was talking about before. But we're going to just work with finite dimensional operator systems mostly here, because for technical reasons, that's what we can do. So if we have some inclusion of finite dimensional operator systems, we can define some sort of index between them as, well, it's the infimum over all lambdas, so that there exists some CP map from the larger one into the smaller one, let's say unidal, since I've, unidal completely positive, so that this map minus the identity map, well, 1 over lambda times this identity map, is just positive. Okay. So this is coming from the usual, or the work of Pimsner and Popa, who gave this interpretation of the Jones index. For an inclusion of subfactors. And okay. With phi being just restricted to the conditional expectation, 2-1 subfactors, I should say. And then, of course, there's work of many other people with extending this notion to other sorts of inclusions of C-star algebras or type 3 factors or things like this. So this is not quite a nice enough notion. So there's a completely positive version of this. So what it is that you're trying to find sort of the flattest map or the least entropic map, the map that most accurately represents your bigger operator system and your smaller subsystem. That's the metric that this is trying to capture. The smaller the lambda can get, the more faithfully this thing is sitting, or the flatter compared to the identity this map is. So it's the same thing, except here you want the correct category, which is completely positive instead of positive. And in his CBMS lecture notes, Popa shows that these two things for the conditional expectation are equivalent for 2-1 subfactor inclusions. For just inclusions of 2-1 von Neumann algebras, there's a difference between them, but for subfactor inclusions, they're the same thing. So that's the notion of the index that I want to discuss. And okay, you can make definitions like this, but then the question is, okay, can you actually do something with the definitions? And the answer is, surprisingly, even in this generality, you can say some interesting things. Yeah.
So the expectation minus 1 over lambda times the identity, if that is positive, then it's automatically completely positive.
That's for subfactor inclusions, yes. It's not true for just 2-1 inclusions. Right. Yeah. So one thing you can show is that, so here's, I guess, the main theorem that we showed or proved. So if you have inclusions, so pairs of inclusions for a finite dimensional operator systems, then under min tensor, you have multiplicativity. Okay. So this doesn't actually use a lot of operator algebras. This uses basically linear optimization, like a minimax theorem. So the submultiplicativity is kind of given by the definition, and then you come up with a dual linear optimization problem that captures the index, and this is where you need finite dimensionality. And you can prove the dual program is also almost by definition super multiplicative, and then the fact that the dual program corresponds with the original one is the minimax theorem of von Neumann, basically. So you get that it is honestly multiplicative. And just as a quick corollary of this completely positive index is stable under matrix amplifications. So here's another problem. So you can just take the index, the positive index, and you can define some new index here just by taking the sup. This is going to be an increasing sequence of numbers. The sup of the positive indices of the matrix amplifications. So does this equal the completely positive index? It sits below the completely positive index by this stability result. But yeah, it could be that there's two notions of index here, or maybe an uncountable number of notions of index. Maybe that's something I wanted to say as just a comment going back here, is that because the min tensor with B of H is defined here in the continuous model theory, another problem is there some sort of model theoretic approach to the fact that the min tensor of B of H with itself is, well, there's uncountably many operator algebras tensor products on B of H tensor B of H. Is there just some model theoretic way to approach this? That's a result of Ozawa and PZA. But yeah, does this thing actually equal the completely positive index? The connection again with logic is, well, if you somehow knew this thing was definable, you would win, but that's yeah, that's a tall order. Something more concrete at maybe even the sort of the C-star algebra level, is this thing just the positive index when you stabilize by tensoring with the Carr algebra? That's also equivalent, basically. Okay. So some sort of stabilization or ultra product continuity result or something like this is pretty much equivalent to this question. But maybe it's also model theoretically possible to maybe just go the other way, since operator systems are very chaotic. Maybe you can just write down some properties, some general properties that the index should satisfy, and maybe there's just uncountably many different indices. I don't know. It seems like it's a hard question. It's probably not definable. So there's probably lots of them, but I don't know how to get a handle on this. Okay, so I probably when you define something new, you should probably explain why it's not trivial. Why isn't this just like the codimension or something like this? That would be brilliant if we just rediscovered codimension or something. That's not the case. So maybe I'll say a little bit about that just to keep everybody assured. So how do you connect this with other things? So one thing you can do is you can define basically this dimensional invariant for a finite dimensional operator system just as the completely positive index of the unit basically in there. And this is multiplicative under minimal tensor. So it is some sort of nice non-commutative dimensional parameter. In just the case of matrices, it gives you n, which that's the correct dimension of a matrix algebra if you're a non-commutative analyst, right? So great. And this actually ends up being the same for the diagonal subalgebra, the massa in there.
Can you just give an example of how computations work? It would be somewhat illuminating, I guess, to just see how these things, why is this so?
Yeah.
That's the computation over there. It's equal to n.
It's not obvious to me.
Yeah, so the idea here is that if you do have this completely positive map, and this is maybe a good segue, but if you do have the CP map, you can always average it over the unitaries. Okay. And you can take convex combinations, and you only improve this constant lambda by taking, well, it stays the same under unitaries, and it only improves under taking convex combinations. Okay. So once you pick like a fixed point for this, you're good. And the only fixed point when you average over all the unitaries for the matrices is the trace. And so you think about what is the gap between the average and the max, and it's like 1 over n, right? So that's really the computation in this, yeah. And actually that leads to another problem, which is, well, for an inclusion of subfactors, does this thing actually equal the Jones index? It's bigger. So the question here really does actually boil down again to, is there some sort of fixed point theorem for completely positive or just normal, if you want, completely positive maps from Mn to n? If you have a fixed point, then that fixed point, when you restrict it to n, preserves commutativity, and that means it's just a linear combination of the trace and the identity. And then you can figure it out from there. So it is just trying to prove some sort of fixed point theorem for unitary averages over the unitary group of n. The conditional expectation absolutely has to be like the most, and or most or least entropic completely positive map from Mn to n. So that's basically the conjecture or the problem. Yeah.
So the tensor product formula that you had, it's only for finite dimensional.
Yeah, only for finite dimensional. Again, if you had some definability or continuity properties under ultra products or things like that, you could just bootstrap it up. But because every operator system just is an ultra product, inside an ultra product of matrix algebras. But don't know how to do that. So maybe an idea here is you look at, and this is maybe just an interesting quantity, but you look at some sort of Pimsner-Popa basis, basically a basis for M as an n module. Maybe you want these things to be positive and add up to 1. And maybe you want to define some sort of entropic thing like sum over I log of trace of xi, or just trace of xi and then log of trace of, well, phi xi, something like this. The fact that there's a lambda bound, there's this lambda value, multiple of the identity bounding this below from zeros, this gives you a well-defined quantity. And if there's some sort of uniform convexity of this entropy function over all Pimsner-Popa bases, something like this. That's probably enough to guarantee that you have a fixed point. I think probably from the interests of maybe quantum information theory, there's some interesting thing going on here if it was like uniformly bounded in some sense, but okay. Yeah.
What if you had Pimsner-Popa basis of unitaries?
Well, that's why I wanted positive ones. So the positive ones that add up to 1. So this is a defined quantity over those. So do something like that. Okay. Don't, yeah. I suppose you could just do it over, well, yeah, there's probably an analog for doing this, but well, no, you really want to define this entropy. So you want some sort of like POVM or something like that. These could just be, yeah, so.
I mean, one of the things is that for the matrix algebra, the index is n.
Yeah.
So it seems to me that I would be surprised if this problem has a positive answer. Because you can take the hyperfinite to one factor tensor with the matrix algebra.
Yeah.
And take the hyperfinite to one factor tensor with the identity inside this. If that index if that CP index is equal to n squared, something goes wrong with that.
But I think in this simple case, it's just, you just get back and it's fine. I mean, stabilizing is okay in this case. So, yeah, I mean, for simple inclusions like group inclusions or just tensor inclusions, it does check out. So like group, subgroup, subfactors, or fixed point subfactors, that all is fine. There's no problem. I just don't know what to do in general. Okay. So yeah, you have the answers you would expect just for these simple things. The really interesting result is that when you look at, for a graph, again, just a simple graph, if you look at the this dimensional function, so the completely positive index of the identity in this E system for the graph, this is an already known quantity. This is the Lovász theta number of the complement graph. So you switch adjacency to non-adjacency and vice versa. This is a well-defined, this is a well-studied object in combinatorics. It's useful in the sense that the theta of the complement is between the chromatic number on top and the click number of the graph on the bottom, and both of these things are NP hard. And this is semi-definite programmable, so up to epsilon, it's polynomial in epsilon error. So it's a remarkable thing that this just kind of pops out. In this case, it doesn't do it for, so this is where the diagonal entries are all equal. If you look at the S of G, where you don't allow the entries on the diagonal to be equal, then you have the diagonal matrices in there, and you just get the cardinality of the vertex set. So, but yeah, this shows it's a non-trivial invariant. This can take all sorts of irrational answers and so on. So it does compute something interesting, even for these simple graph type systems. And in fact, there's already some sort of, for quantum graphs, there's already which are just subsystems of the matrices. There's already some quantum Lovász theta that was defined by Duan Severini and Winter in terms of complexity of communication for quantum channels. But the problem here is for general operator systems, for graph systems, these things, there's an agreement. There's a dictionary between these two. But for general subsystems of the matrices, this is only defined for subsystems of the matrices. I'll just say what it is. It ends up actually being the CP index of this system inside of the matrices. So it's the flip. These two things end up being equal to each other. But I don't know if there's any correspondence between this quantum Lovász theta and this dimensionality parameter for a general operator system where the complement of like the operator system version of the graph complement, you just take the orthogonal complement of your system and then you add back in the units. So it could be the case that there's actually like a pair of different notions of dimension or quantum dimension or index for even matricial systems. That could very well be the case. These two things, I don't see why they would agree, but I don't have an example where they disagree either. It may be quite simple to come up with an example, but I tried a little bit and it's, well, I feel like it's a little bit subtle. So, but yeah, so there might be multiple notions, and they satisfy the same formal properties. So they're even at the matrix level, there might be sort of multiple notions floating around. I don't know. Maybe just the last thing I'll say is just another computation that you can do here. So there's a lot of similarities actually between graphs and generating operator systems for discrete groups. So let's, instead of G, let gamma be a countable discrete group. Let's just say finitely generated. Discrete group. And you take some finite generating set, which is equal to the inverse and contains the identity. So you can look at this operator system inside of the reduced C-star algebra of the group. It's a perfectly good finite dimensional operator system. And you can compute what this thing is, and actually it parallels in a remarkable way what happens in the graph case. So the answer here for this dimensional number is it's again the minimal lambda, so that this map phi lambda, which is defined on the identity to be 1 minus 1 over lambda, and then or I should really say inf. So I guess it's a min. And it's minus 1 over lambda for every non-identity element of the generating set. That this extends to a positive semi-definite function on the group. And so this ends up being, there's like, there's many definitions of Lovász theta. It's one of these things where you try to come up with a reasonable graph parameter that uses like positivity, and it just all goes to the same place. So there's another definition of the Lovász theta for a graph that this like precisely copies in this this kind of this generator subsystem for the reduced C-star algebra. And basically the reason is that in both the matrix case and the group case, you have some sort of co-multiplication. The map that you're looking at in the matrix level is not really a co-multiplication, but there's a complete order isomorphism of a canonical one from the matrices into the matrices tensor themselves that is like maximally entangled in some sense, and the co-multiplication on the group is also kind of some maximally entangled complete order embedding from the group into the tensor of the group with itself. So there's some very interesting parallels that are going on, and it's something I've been thinking about. I think there are interesting things to say, but I won't say them now. I don't want to cut into anybody's lunchtime, so I think I said basically what I wanted to say. So I'll just stop here and thank everybody for listening.